Under the guidance of Dr. Mueller and research assistant Ibrahim at BIST, our senior design team has manufactured a tendon-based actuation system for a soft robotic bat head. My name is On Lee, and my team consists of myself, Jason, Joe, Ritish, Sam, Tianyu, and Ryan. Horseshoe bats have highly accurate sonar detection in dense vegetation to capture prey in low visibility. The goal of our project is to implement this technology so that a drone can fly autonomously through dense vegetation. Horseshoe bats, specifically Old World horseshoe bats and New World leaf-nosed bats, do this by emitting biosonar pulses that are diffracted by biological baffles called noseleafs.
Horseshoe bats can move their ears, called pinna, to deform for biosonar reception. The pinna and horseshoe bats have more than 20 muscles related to complex motions to improve sensing and navigation performance. The noseleaf and pinna motions create Doppler shifts. These Doppler shifts allow horseshoe bats to identify prey in dense foliage with active biosonar. Horseshoe bat pinna create many distinct pulse sequences to create Doppler shifts. To replicate these muscles and Doppler effects, biomimetic ears have been manufactured with tendons to allow for precise soft-robotic actuation of localized areas.
Compared to the previous pneumatic actuation method used for the soft robotic bat head, the tendons more closely mimic muscles. This allows for greater control and maneuverability of the pinnae and noseleafs. With tendons, the bending can be controlled with an analog input instead of binary input, which allows for more combinations and movements. Where pressure control is nonlinear, tendon control will allow for more precise numerical control and distance bent. Another advantage of tendon control is that it is quieter than pneumatics, thus reducing noise in sonar data collection.
Compared to the parallel pneumatic control design, the tandem actuated system will actuate a smaller pinna and noseleaf, which more closely resembles horseshoe bats. Our pinna and noseleaf are 5 cm tall and 3 cm tall, which is about 2 times the size than that of the greater horseshoe bats. This size is reduced from previous system, where the pinna and noseleaf was 7 and 5 cm respectively. We can achieve this reduced size because the tandem actuation has the smaller components.
The current model is manufactured with a silicone skin and rigid core with tendon sheets routed between the two to guide the tendon and protect the silicone and rigid core from the friction and potential tearing from tendon movement. Originally, the team considered using a hexagonal core base. However, the problem with the hexagonal core was that it had a short life cycle due to the bending direction. The linear bending direction, we found that multiple square bases oriented like finger joints is more effective. The silicone skin provides a smooth surface similar to that of a bat pinna so that biosonar signals can be processed without interference from the shape of the rigid core.
The tendons replicate the muscle movements in the pinna and noseleaf to form the structures. The rigid core provides a stiffness and control to the pinna and noseleaf. Our tendon actuated system replicates how horseshoe bats move their muscles, but with 5 degrees of freedom in each pinna and 3 degrees of freedom in the noseleaf. Our movements will also take place within 100 milliseconds. An actuation system, consisting of 13 times larger and 13 times smaller, is used to actuate the pinna and noseleaf.
The bigger pulleys are connected directly to the servo motors. The tendons are then connected to a fixed point in these larger pulleys and move when the servo motors are actuated. These tendons are then routed to the anchor points on pinna and noseleaf through smaller pulleys to provide the actuation. The tendon sheath used between rigid core and outermost skin provides a free way for tendons to move and eliminates the friction between outer skin and rigid core due to tendons. The pinna and noseleaf are held in place with 3D printed holders so that tendons have a surface to pull against. For future research, our tendon actuation system will be used to optimize the pinna motions in the bat ear for processing incoming biosonar signals. Thank you.